Welcome to section 11.6. This is our first example. It's probably best done through examples in terms of explain because there's no real new concept that's going on here. We are just solving systems of equations, and we would do it in the same manner that we would do linear equations, but all of these will have some nonlinear aspect of it. So if you look at the first equation that's given in 11.6 number 10, it's y is equal to the square root of x, and that's a nonlinear equation. Now it's being matched with the line y is equal to 6 minus x. And so our job is to solve this system of nonlinear equations. Both of them don't have to be nonlinear, but like in this case, but often they are. And so let's take a look at what's here in number 10. How would we do this? Pretty nicely. We're going to do it, usually it's done by substitution. I'd recommend that way more than elimination. And so what are we going to do? Well, we have y solved for in the top equation, so let's just put that in, and just for emphasis, I'll put that in a new color. So we know y is equal to root x, so now we're going to plug that into the second equation and force it to happen. And as we force it to happen, we'll have an equation to solve. Well, we need to solve for x, so we got to get that x out from underneath the square root. So we're going to square both sides and get an x squared is equal to 6 minus, not an x squared, right? The squaring removes that square root, so we get an x is equal to 6 minus x, the quantity squared. Or that's x is equal to 36 minus 12x's plus x squared. Well, we know how to solve for an x when it's in a quadratic. We move it on over. And so we move it over and we get this number. 0 is equal to 30. Well, let me rearrange that at the same time. We start with our x squared. Bring over an x. It's going to add another x there, so negative 13x's because we subtracted it over and matches with that negative 12. And then we'll put the 36 at the end. We know exactly how that factors, and I think you'll find that most of them factor. It would be pretty mean to give you ones where they used to have to use the quadratic formula, but theoretically that's possible. Factors of 36 that add to be 13 we know are 9 and 4. And both are negative in the factorization. That means there's two answers. X is equal to 9. And x is equal to 4. So there's always a question of whether we have extra solutions, extraneous solutions. And so let's see about 9. Could 9 work? Well, we're going to find out that 9 really can't work. And the key is right back up here. In order for these two equations to be solved, we would need to be able to have this statement right here hold true. And so if you check in any one of the originals, they work independently just fine, right? That you could take the square root of 9, you could take the square root of 4, you can take 6 minus 9, you could take 6 minus 4. But the problem is remember, we're trying to get them to work together. So when we put them together, is it possible for the square root of x to be equal to 6 minus x? Well, let's check that out. If x is equal to 4, we would have the square root of 4 is equal to 6 minus 4. Well, that's a true statement, right? But if we tried the 9, so 4 is a keeper. So x equals 4 is a keeper. And if we try the 9, though, look what happens. We get the square root of 9 needs to be equal to 6 minus 9. It's this part over here where you get the negative 3 that's not going to happen, because that's the principal square root. And so 9's not an answer. So our only legitimate answer is 4. And if you use 4 and plug it back into any of the originals, you'll get a 2. So 4, 2 is the common point of intersection. So what's nice about these, they're asking you in the first set as you go from 5 to 24 to do a graph. And one of the reasons is so that you can understand your answer. So we knew about these guys. Let's go graph them. Let me just rewrite the equations. They were y is equal to the square root of x, and y is equal to 6 minus x, right? Those were the two original equations. Let's just graph them independently. 6 minus x, 1, 2, 3, 4, 5, 6. There's our 6, down 1 to the right 1, because it's a line with the slope of 1. There's that second equation. I'll do the first equation then in blue, right? That's the square root of x. What does that look like? that looks like this. And you can see what we found in our answer. I'll put it in green as a dot. We found the point 42 as the only intersection point. So what's awesome is that you can start to realize, well, where did this 9 come from? It's not arbitrary. It's totally coming from the fact that when we squared both sides, we lost the sight that we had a principal square root, which means the parabola could have had another side, which I'll put in red. Right? And if I put it in red, guess where that second intersection point is going to come? It's going to come at a x coordinate of 9, and that's where that 9 is coming from. But because we're just dealing with the square root, this red part is not even here, and that is why we're only getting the solution of 4. But why both are coming out algebraically, because the moment we make it bigger, the moment it doesn't know what we originally had. So we always respect that initial point. So I wanted to talk long about that in the first video, just so you can start to try to understand your solutions rather than just come up with those solutions.